Thank you so much for having me. It's really humbling to be here and see all the work. My name is Dana Cupkova. I'm an associate professor, I almost slipped, recent associate professor at Carnegie Mellon School of Architecture. And I'm a track chair at Master of Science in Sustainable Design. And I'll be talking about kind of attunement, two-hour attunement through low-tech materials, thermal perceptions, and all things non-kinetic, just for change. So I am an architect, I'm a designer. Concurrently with my academic position, I ran a practice, a design research collaborative called Epified Lab, which is focused on the design of built environments through lens of thermodynamic behaviors. Truly operating between practice and academia, there is a structured yet slightly ambivalent relationship between the set of categories that want to engage context through very different formal behaviors, data metrics, and use of code, but vary in scale, type, and materiality. So on the side of the Epified Lab, we produce experiences and academic research and teaching. We focus on kind of procedures and methods that get us there, but collectively the body of work situates architecture as a kind of ecologically reactive form, primarily drawing connections, relying on simulation, relying connections between perceptive form and its contingency on invisible forces. Focused on energy, and energy is both empirical and perceptive. My work really looks at a definition of a thermal comfort away from the industry standards that are really underlined by underlined by engineering of mechanized building systems, and looking towards the capacity of architecture to trigger these perceptions through subjective experiences. And I don't know if you know, but thermal comfort is an engineering term which is based and calculated on a metabolic rate of humans. So we're already using these standards, like ASHRAE thermal comfort is based on the kind of scientific research into human body. Yet, unless you are a 40-year-old white male, the building is really not designed for you. So you need to kind of, it really doesn't care how you feel. So in terms of kind of the, and Axel talked about it a little bit, the kind of a preconceived ideas about how building systems are integrated, it's highly problematic. So this is a 9-year-old project now, Sioux House, that originally served as a proof of concept and jump-started a lot of my currently funded research, primarily with industry. That looked at the geometrically actuated thermal mass. So this is a house which has no mechanical air conditioning, and it's cooled passively through this chunk of concrete. Ironically enough, we got lower LEED rating system for this one because we had no innovated air conditioning. So that was quite interesting. So it led me to this idea that it's actually surface figuration. It's a significant factor in thermodynamics of passive building systems, primarily due to convection, and this has been published, so I'm not going to go too deep into it, but we're essentially, through both simulation and physical testing, we're able to isolate the heat transfer coefficient of these different shaped surfaces based on geometry. So I'm able to start associating the currently engineering method of looking at the thermal mass doesn't really take shape, or a lot of the simulation, energy-based simulation, don't take shape into the consideration. So we were able to determine kind of a basic rule set for geometrically actuated time lag that would kind of have significant effect on environmental dynamics in regard to decreased reliability of mechanized environments. So now we have ability, and this is sort of a new venue, we have ability to start identifying these figures and geometric trends, which there's a lot of information about them, and assign them kind of a potential thermal values and do some statistical analysis to start generating new sets of geometries with desired thermal lag and a kind of new set of tactile experiences that were kind of, this is a new line of inquiry, that we can sort of use machine learning as a way to start kind of projecting some of these performances. I mean, this is a little bit of an ode to concrete. And as you know, manufacturing of concrete is has the biggest effect on carbon production and greenhouse gas production. But so we collaborate with industry quite a bit. We have manufacturing innovation funding from Carnegie Mellon University. But what's ironic about concrete is that concrete essentially has one of the most benign embodied energy footprint on carbon per unit of material. And the main culprit in this whole problem is the cement. So we're starting to look at the kind of a holistic production of material mixtures and demolding the process of fabrication within some of the industry partners we're dealing with, so we can kind of have a much greater impact in terms of the industry itself. So this kind of nuanced understanding of surface ductility and thermal choreography offers sort of two lines of material research of architecture as it relates to both ecology and technology. And so from outside in, there's a sort of opportunism of existing phenomena related to material weathering, and a lot of projects talked about this, which I'm interested in kind of from shifting away from a positivist humanist concept of industrialization and investigate modes of ecological disruptions into the new material modes. And this is also in context of one of our manufacturing industry partner. They're always like, the main production or main effort in their research really go into trying to prevent these situations. So the whole idea is, how do you start engineering materials that enable completely different kind of through kind of porosity, ingredients, ductility, different kind of intelligence about aesthetic, biodegradability, and holistic ecological experience about large-scale buildings. So that's sort of an outside in. And from inside out, the Natter inquiry, we're engaging kind of a thermal color as a means of communication with environment, so thermochromics as well, unpacking ideas of thermal comfort in buildings. And the focus is really on reactive surfaces, and 3 minutes, and thermal communication, proposing thermoregulation to operate more, for architecture to operate more as a mood ring. And this goes back into idea of mechanized environments. So rather than optimized engineering system, how this can be kind of an overlay of previously passive geometries together with these active thermal networks, with possibility to create pathways and embedded connectedness to specific forms of biofeedback, and this is very interdisciplinary kind of research agenda, while using human physiology and emotiveness as a way to kind of react or communicate with the environment itself and inform design of material expressions. So this is a little corny, but it's a kind of a projecting of these scenarios related to human presence and a state of mind into the materiality of surfaces and spatial character. This is our first functioning prototype. This is a piece of concrete using thermochroming and heated pathways. So we're looking at a different kind of way of producing these sort of distributed control systems that then allowed us to set up hierarchy of testing procedures and modeling workflows to simulate changes in microclimate in response to the human thought, and produce kind of more robust pieces of proof of concept using thermochromics, programmable electromechanical controls to affect surface temperature, tactility, while using the sort of a distributed matter and sensory effect rooted in thermodynamics. So this is a final prototype we currently have. The thermal pathways are currently programmed, and we're still working on this is sort of a second part of research. We're taking on a kind of what is the method for communication and actuation of the system. Thank you.
Very cool. I have a...
Thank you.
I have a
That was without coffee.
Pardon?
That was without coffee.
Can you explain the relationship between the form and the environment, or why do these pieces look like they look like?
So I didn't want to get too much into it, but it essentially, I have about 2 tons of concrete in front of my office, which are 50 tiles which weigh the same and have same surface area, but completely different figuration of the surface. And it was a measured experiment to essentially prove that we heated them and then cooled them, and all of this was sort of in 2 slides. The idea that so engineering understanding of thermal lag or material thermal conductiveness it's based on mass, surface area, and material. There's no geometry. If maybe I'll go to this one slide really quickly, but essentially, if I have 3 tiles, which are, if there were thermal mass system, just like the building we built a while back, and I measure their rate of heat transfer, the geometry completely changes the heat transfer. And I can shift the lag by 3 hours just through the geometry. So the geometry itself, I'm just going to, so these are kind of a thermal maps of 3 tiles. It's kind of a visual comparison very early on. This is a 2014, I think. Those were physical experiments where we sort of measured the daily cycle and rate of heating and cooling. So the geometry itself is because of convection. So because of, and I have this whole theory of a thermal pocket, that we're essentially looking at geometry. We have a way of looking at geometry and predicting to some degree the way it's going to behave. So this is a part of the measured experience. So, and a lot of this comes from the sort of a bigger ambition of thinking about kind of a, Frank Lloyd Wright textile block houses, the sort of a cradle-to-cradle resource material. 30% of the world is climatically and materially sort of at the position where this sort of idea of earthly materials and construction from that with like no mechanized system is completely possible and feasible. And so we're kind of looking more into these low-tech ways of thinking, using technology as enabling and accessing this in a large scale. So, and geometry is a pretty big factor in that as well.
Thank you so much.